Okay, at this point, this is part 2. You should have your binary tree code ready to go and be able to follow along. We're going to be actually adding and doing some other ones. We're going to have a video too, but we've ported and got this code to compile from the example code that I've given you. And we are ready to set a breakpoint and kind of test and go through each portion of it. So the only thing that you really need to be aware of at this point is this guy right here, this root node. That's where everything begins. And in fact, the first call to the insert function, what they pass in is the address of the root. So remember, they're passing the pointer by reference. The pointer has to go by reference. So it's a double pointer. And that's why you have this star star here, because root is a pointer and you're passing root by reference. And you have to do that because if you make a copy of, if root is just a copy, then that means that its addressing is all going to be messed up, because it'll pass the pointer by value and it'll make a copy of the pointer with a different address, but having the value of where it originally pointed to. So you got to pass the pointer by reference. And it just basically, it works the same way, because we're going to be manipulating the root pointer itself from the first root pointer that is put on the stack. And we're referring to this guy when we pass it by reference. Instead of passing it by value, which would be, we get rid of this ampersand, and it would make a copy of that root pointer. And essentially, when you think about the root pointer, here's the address of the root pointer. Here's what the root pointer points to. If you make a copy of the root pointer, what you have is the copy comes in, and initially our root pointer is going to point to 0. But if the copy comes in, and the address of that copy right here is going to be different, but it's still going to hold the same value up here, but the address is going to be different than the original root pointer. So then it's just a whole nother root, pointer that has the same value inside of root, what root is storing or what it's pointing to, but the address itself will be different because it's a pass by value, meaning it makes a copy of the root pointer. So it's not the original root pointer we start out with. So that's why we have to do a pass the pointer by reference. And when we start making our links in here, that's also why we have to do a pass the root by reference, is so that the copy of root's not made with a different address on the stack. So essentially we have a copy of the root pointer with a different address, but it holds the same value inside the original root pointer. And I guess I just explained to you why we have double pointers. Okay, so let's go ahead and move into actually traversing this code. Finally, we're actually there. And what we're going to do is I'm going to set a breakpoint in main for the first insert. Okay, we're going to insert the number 10. Okay, well, let's go ahead and run this. Okay, now, so we're running the binary tree. Now notice here root is null. Root points to 0. And our count is 0. We're not going to be dealing anything with count right now, so don't worry about the count. Because it doesn't really matter. You don't really need to keep track of the count of a binary tree, because it's self-referencing. This is also it stops based on pointers, so we don't need the count. We probably get rid of it, but I'll just keep it there in case we want to add something with it, just so that we know how many leaves are on the tree. Okay, so we insert 10. So let's do a step into. Okay, so first thing is we're passing that 10 value. And the insert, this is the actual function that inserts recursively. And we have to pass this root by reference. So we're not passing a copy of this guy that's been created on the stack. We're passing this guy that's actually on the stack that's going to point to our first node. Okay, so right now, when we pass root in, you'll notice that it's null. So if we go to add watch, actually we probably could doing locals, but let's go ahead and do an add watch. Yeah, right here. Okay, so we actually have to go into it before it comes in. So we look at root and it's null. So what then happens is we're actually going to run the insert node helper, sending it the value 10 to store in the new node, and we're passing the root pointer by reference. And the root pointer is holding the value 0. So right now, our root pointer has the value 0. That's why I'm leaving it empty here. If you see empty, you know that that's pointing nowhere or 0. And on the stack, our original pointer that was created inside of our B tree has the address 10. And it's being passed by reference. So when we actually go into the insert node helper function, it's actually the root with the original address that we start with. Okay, so back to debug. We're going to do step into here. Okay, we've passed root in as this guy named pointer. So root right now is null, it holds nothing. So this is just like our head pointer in our linked list. If we have no nodes on the list, then we're going to start our list. And our data is coming in as the value 10. So if this pointer that was sent, which happens to be root, has null, or it's storing nothing, that means that we take that double pointer, dereference it, and if it has 0 as its value, that means this guy right here, if it has nothing, just remember, put a 0 in here in your head. That's pointing nowhere. If that root pointer, or that pointer that was passed to that insert node helper function, has the value 0, then that means that it's not been linked. So we're going to create a node for that. And that's what we do. If the pointer or root at this point has nothing in it, then we're ready for a new node. So we take and we say, okay, pointer, you're going to be equal to a new node off of the heap. And we pass in the data that we want to be stored inside of that new node, which is the value 10. Uh-oh. I'm going to make a change because this is going to be confusing. Because I've got 10 being stored here, and we're going to be putting 10 there. So let's say that let's say that the address is 100. The address of root is 100. Let's do that. Okay. So let me go ahead and add an extra 0. Okay. Actually, it wouldn't be too bad to do this, but okay. So actually, 10 is not going to go here. Excuse me, I misspoke. Okay, so this pointer is, this node is created. All right, so step over, and bingo, we put our first node on the list. Since root is somewhat out of scope, this actually is root. So you see that it no longer has nothing in it. And its data is 10. So the root pointer points to this node. Okay, so once this line on line 89 is done, this step happens. We get a new node. And let's go ahead and remember, just like our linked list, every node has a left and a right. So what's going to go in the storage of this node is 10. And then we're going to have a left pointer and a right pointer. Okay. Okay, now this is going to be for what the left and the right pointer store. And remember, they have their own address, so we're not really worried about this. For the left and right hand pointers, yes, it's important when we pass them by reference. Actually, you know what? Let's leave it. So this is going to be right here. This is going to be what the value of the pointer, the value points to, what it points. And this box is going to be here, the address of the pointer. Okay, so what it points to and the pointer's address. So it's just basically one of these guys. That's all it is. It's left with its own address and what it points to. Left with its own address and what it points to. Right with its own address and what it points to. Okay, so since we've assigned root to be the new node, the operating system finds an address for this new node because the node itself has an address. Okay. I'll go rid that up. Now let's see if I can get this now. Okay, I'm going to pause real quick and come back and see if I can't get this drawn a little bit better. Okay, so we've got it. We've got our left and right pointers that are just like this, that are going to be pointing to the left or the right for our binary tree. And this is going to be our root node. And it's going to be assigned an address off of the heap. So let's say that the address is 2. So that means that this root pointer is going to point to 2. So it's linked to this guy. That's what happens. Now remember, this left pointer and right pointer, let's say that this one has the address of 3, the left pointer on the stack has the address of 3, and this one has the address of 6. And remember, it's going to 0. It's going nowhere. So they point nowhere. And that's done in the node code. So remember, that's done up here. When we create a node, we set left and right to 0, right there. Okay. So back to our drawing. Left and right go to 0. So remember, I'm going to leave those blank. And eventually I won't even talk about these guys. These are the addresses of these pointers itself. This right here is the address of the whole node. And what is inside the node is the value 10. So we go over here. And that's what happens with this line. All this stuff that I've drawn out here, the root node storing the value 2, pointing to the node that has address 2, that it contains the value 10, has a left and right pointer just like this pointer that has their own address, but also points to the address of what would have been the next in the previous and the linked list for a linked list. But this is now going to point to the left and the right. Okay, so that's the first one. Now we're going to get into the next one, which is going to be where we essentially, if we were to finish this, that's it for the first one. We're done. So now we're going to do another insert, and this one is going to be my tree dot insert 15. Okay, so I'm going to set a breakpoint here. And we know that this is currently what we have for the binary tree. Okay, so we run the insert again. The value 10 has already been inserted into a new node. Now we're going to insert the value 15. Now notice here, we're passing the root again. So we pass the root again because this function, or all of this, is done recursively. So we pass in the root again, and with the data that we want to store. Because every time you do an insert into the binary tree, you start from the root. Now this is okay for efficiency because binary trees will be built to the side. So essentially, before you use binary trees, they're already going to be built and inserted into memory. So we have storage of 15 going into our binary tree. We pass root to begin with, and this time root is not null. Its left and right are null, but root itself has or the pointer points to a node that has the data 10 in it, and it has an address. So let's step into this, and the first time this runs, root is being passed. So essentially, we are going to run this insert node starting with the root, and since the root pointer that we passed is not 0, meaning, hey, let's run this insert again, we're passing this pointer again, we look at it and we see, oh, it's not 0, it's 2. Okay, well then we got to find where this goes. And what ends up happening is we then link it. So if the value that we're sending in, we look at the value of this guy right here, 10, and if we are sending in 15, it's greater than 10, so we want it to go down the right. If we were sending it 5, that's less than 10, it's going down to the left. So you can do this with names too, with string compare, where you go down the left or the right depending on the lexicographic comparison using string compare of a name. So you can use it for any value. So you're sorting and you're making your links dependent on the value of what you're sending. So let's look at how this works first, and then we'll kind of continue with it. So root is being passed first. It's not null. So we're going to go ahead and continue. And what we're going to do is we're going to compare, is this new value, 15, that we're sending in for a new node, is it greater than the value of my current node? All right, so 15 is the new one. 10 is the old one. So what this does is it's making that comparison. So let's go back to the actual the drawing here. So this line of code, line 98, makes the comparison. Is 15 less than or greater to 10? If it's greater, it's going to run the function again recursively, but it's instead of passing the root by reference, it passes the right-hand side pointer by reference and recursively. So this runs again with us passing the right-hand pointer, which currently is null. So the pointer that we're referring to right now is root. So we're referring to the root node, this guy right here, but since the value coming in, this already exists, and the value is greater than what is already here, that means we're going to send it down the right-hand side. So we're going to do that recursively by calling on the root's right, which happens to be this guy, and it's holding 0. So it's a recursive call, passing in the right-hand node. So we're going to do a step over. It's not less than. So we're not going to the left. It's greater than. So 15 is greater than 10. So we're going to run insert node helper again, but get this, we're passing the right pointer of our root node by reference. And remember, it has to be by reference, because if we didn't do by reference, that means that when we pass this guy, we're not going to get the address 6 of the original. It would make a copy of that with a different address, and it wouldn't be linked to this node at all. So that's why it has to be passed by reference. So we're going to pass by reference. And let's go ahead and go back to the code. Yes, 15 is greater than the 10 value. So we're going to pass the pointer node or the root node's right-hand side by reference. And when it goes inside this function, and I'm going to run this function now, here's my little arrow. I'm going to do a step into right here. Now it runs all over again, and this pointer happens to be no longer the root. It's this guy right here. It's the pointer, the old pointer's right-hand side. And that's why we pass this down. So now this function runs all over again, and it happens to look, and we send it the right-hand pointer, which does have the value 0 in it. So we found a place to put our value 15. So that gives us another node. So we'll get to this point here in a second. Let's go back to the code. Okay, so since we're passed in the right of the root pointer or the previous pointer, our current pointer is empty, so we found a place to put that value 15 in the list. So then we just create the new node, passing it 15. And that goes on the heap. The pointer is the right-hand side. Now it contains 15. So what we've done is we've done this. We've created a new node. Get the writer out. And this new node let's say that it returns the address 7. And that's what's going to go right here. And this one has a left and a right. Now remember, I'm not going to put these guys in here anymore. Just remember that these guys, that's why we have to pass it by reference. The pointer by reference is so that these don't change, the address of the pointers themselves. So this right one is going to point to nowhere, 0, and 0 again, and then 15 is going to go here. Pretty slick, huh? That's actually pretty slick how it works. Okay, so let's do one more, and then I'm going to let you play with it. So seriously, here's the best way to understand this. Go through it just like I'm doing. Just like I'm showing you how to do. And once you start going through it, you'll start understanding it better. Now, the recursion part of this isn't so important until we get to the printing of the list. That's where it gets to be an issue on understanding the winding and the unwinding of the stack. But this one is pretty simple. So let's run another one, and then we'll probably call it for until video, the next video, which will be coming, where we do traversal of the list. So let's do another insert, and let's finish this one out. So we go ahead and do a step over, and that is done running. And this is where it's unwinding. So it unwinds all the way back to the last call, the last recursive call, and then it's done. Okay, so let's do another one right here. My tree. Dot insert. Let's do 12 here. Now this is where you're going to really see the binary tree work. We're going to set a breakpoint on our new insert. Okay, so currently this is what we have. Remember, these guys are pointing to 0. This left hand is pointing to 0, but the right hand we've linked to this node right here that contains 15. So you can see that we're actually inserting them in order, which means this is how a binary tree works. Is you could have a left link if you're going to insert, if 5 was going to be inserted, but it would go down to it would be onto this side. So let's get into the code and see how it works. And then I'm going to show you how to draw a tree. And then I think we're going to be, an insert tree. And we'll do that with just regular numbers. Okay, so this is our binary tree currently. We're going to do our next insert, which is going to be the value 12. So we go in, and notice how we're passing root again. So we step into it. Root comes in. Root is not null. So we're trying to find a place to store 12. So I need to go and look at roots left or right. So here is now where I'm at. Roots left or right. We got to look at it and see, hey, does 12 belong? Where does 12 belong? Well, the algorithm is if it's less than the current node's value, you go to the left. If it's greater than the current node's value, you go to the right, recursively. So in this case, 12 is greater than 10. So we're going to go down the right side. So let's look at how that works. We say, okay, pointer's not null. We have the value 10. Is 12 less than 10? No. So now, is 12 greater than 10? Yes. Run it again, but get this, we're passing the right side by reference. And in this case, the right side has a value in it. It's not null. So this function is going to run again. Okay, so let's go back to that. We've decided that yes, the data is greater than 10, so we have to go to the right. Now we are going to pass it by reference, the root pointer by reference, or the right pointer of the root pointer by reference. So we're going to pass this guy by reference. And then remember, we have to take the reference of the pointer, so we don't change this value. It doesn't make a copy of the pointer and change the pointer's address for our links to actually work. This now is what's going to be passed, because 12 is greater than 10, we go to the right. If it was less than, we would go to the left. Okay, so we now have recursively called, and pointer here, now look at that, it's not null, it's the 15 one. So now we're dealing with this guy right here. This is the pointer we're working with now. And we look at the value of 15, and we're going to compare it with what we want to store, which is 12. So we come back to the code. It's not null, so now we need to go and say, hey, do we go to the left or right? Well, the data is 12. It is less than the 15 that we're currently at, which is right here, since we're dealing with the node that has 15 in it. So then what we know is that since our current value that we want to store is less than, or the value that we want to store is less than the current node we're visiting, then we need to recursively call this function again. So I'm going to do a step into. Now here, notice this, we're passing the left. So if we look at this guy right here, we notice the left is indeed null. And so is the right. But since 12 is less than 15, we're going to go and run the insert node helper again, but we're going to send it the left pointer. Okay, so this is going to run. I'm going to do a step into. Okay, now notice how it came all the way up here. The runtime came all the way up here. It's because this whole function ran again, and we passed in the left, and you see it's null. So we're actually looking at, we've run the function again, and our current pointer is now this guy right here. Our previous current pointer was our 15. But now we are dealing with the left hand as our current pointer. And notice that it's null there. So we're now traversing the left, or we're inserting to the left, and we found an empty node that we can put our 12 after following all the greater than and less than rules. So we found a place to put that 12. So we see that the left pointer of the node that has 15 in it is null. So it's time to find a home for it. So that 12 now goes in there and we create a new node. So this is what happens. New node is created. Okay. And let's say that it's going to have the address, now let's say 20. That's fine. So that means this left node is going to point to that address. And the value 12 will be in here. And of course, it's going to start out with the left and the right hand side that has 0 or pointing nowhere. This guy over here is pointing nowhere. Oops, I messed that up again. I wish I knew what was going on. Oh, there we go. And this guy right here is pointing nowhere. So those are waiting for links to happen. So if we inserted a 5, it would say, oh, the 5 is less than 10, and it would put it over here. If we were to insert an 11, it would go and look, oh, 11 is greater than 10, go over here. Oh, 11 is less than 15, go over here. Oh, 11 is less than 12. Oh, we found a home for it. So that's kind of how a binary tree works. So essentially what we talk about when we're inserting trees is if you were to take the values 1, 2, 3, 4 and insert those in a tree, you would just be going to the right, to the right, to the right, to the right. You would have a fancy linked list. So the key to a balanced tree is for your values that you are putting to be well balanced so that that left and right mechanism builds a nice tree that's fanned out like this. And your root node starts here, and you got your other nodes that are linked together, that are linked, and then some of those come out that are linked, and so forth, and so forth. And that's kind of the way that a good balanced tree works. Is because the data as it's going into the list is sorted, but in a balanced way, so that the more data you have, the quicker you can get to it. Okay, so let's take some values and let's do a binary tree. So I'm going to take our first 10, 15, 12. 11, 4, 20. Okay, so 10 is our root. So that goes in first to the tree. Now this is 15. It may not look like 15, but it is 15. There, that's a little better. So when we go to insert the 15, we see that it's greater than 10. So it goes to this side. That's where 15 is stored. Then we go in 12, it's greater than 10, but it's less than 15, so it goes here. Okay, and then 11, it's greater than 10, less than 15, less than 12, so it goes here. A 4 is less than 10, so it goes here. A 20 is greater than 10, greater than 15, so it goes here. And each of these have the ability to go left and right. And the better you've got your tree like this balanced, depending on your links, that's what we call a balanced tree. So often when you're building trees, you run it through an algorithm that balances the data that you're going to insert. So Google will go out and get all the data from the websites, sort that data so that it creates a balanced tree, and then inserts that data into the tree, and then makes those binary trees searchable. And that's the secret to Google's success. That's where they took over the world. Well, part of it. Amazon might be pretty darn close, but this is what changed everything in computer science. Binary trees and big data. That's why nowadays you have everything at your fingertips. Before, none of this was capable of happening through hash tables or a regular linked list or anything, because it just did not have the capacity to hold a lot of data, access it quickly. And that's what binary trees do, is give you the ability to have a lot of data and access it quickly. And it's the true way things are done. Okay, so run the debugger, practice building your own trees. The next video, part 3, I'll probably be doing, it'll be coming up, and I'll post it, of course, in the same spot. So other quarters will have access to it as quicker than some of you listening right now. But all right, that's it. That's binary trees, part 2. Part 3. Watch part 3 for traversing a binary tree.